All right, for this last one, starting off, f of x equals x squared minus x minus 2 over x minus 1. First thing we should do is, well, let's see if we can factor it at all. So if we factor out the numerator, x squared minus x minus 2, we end up with x minus 2 times x plus 1 over x minus 1. So we factored it out and unfortunately found out that, well, the factors don't cancel out. So it was a little fruitless, but that's okay. So looking at the numerator has a degree of 2. The denominator has a degree of 1. Now if we go back a couple pages to when we talked about horizontal asymptotes relating to their degrees, down here it says if the numerator's degree is greater than the denominator's degree, there's no horizontal asymptote. Huh, interesting. We might have to run into some, or we might have to do something about that in a little bit. So there is no horizontal asymptote. For our, I missed it. There we go. For our y-intercept, we're going to plug in x equals 0. So we'll do f of 0, giving us 0 squared minus 0 minus 2 over 0 minus 1. So after we simplify the numerator, we get negative 2 over negative 1. That gives us a y-intercept at y equals 2. Let's plot that on our graph. So at y equals 2, we got our y-intercept there. For our x-intercepts, we got to set that numerator equal to 0. So the x squared minus x minus 2 equal to 0. Well, we already factored that out. Let me zoom back in. Sorry. We already factored that out looking up at this part up here. I just tried pointing to it. Sorry. This part up here, we already have it factored. So it's x minus 2 times x plus 1 equals 0. Which means our two x's that make it equal to 0 are x equals 2 and x equals negative 1. So let's plot those. So at x equals positive 2 and x equals negative 1. Those are where it's going to cross our our x-axis. The vertical asymptote. What makes your denominator equal to 0? So x minus 1 equals 0. That gives us x equals 1. So we're going to have a vertical asymptote at the line x equals 1. So if it helps you to draw like a dashed line through there, or if you want to draw a highlighted line through there, that works. And so that's going to be our vertical asymptote where the graph is going to get really, really close to, but never quite touch. Let me draw it a little larger with my highlighter. Cool. Now, the next part, it says slant asymptote. We haven't talked about that. So for our slant asymptote, the directions I'm going to give you are, that's a shape, divide and ignore the remainder. So we're going to divide and ignore the remainder. So we're actually going to do the division of x squared minus x minus 2 over x minus 1. Now, to do that, we can use synthetic division because we have that linear divisor, that x minus 1. So we're going to put in the box the 0 of that divisor, which is just x equals 1. And our coefficients are 1 from the x squared, negative 1 from the x, and negative 2 from that constant. So we're going to drop the 1, multiply by 1, we get 1, add those together, we get 0, and then multiply that by 1, we get 0, add, we get negative 2. So again, we're going to ignore the remainder. So what this translates to, this 1 and 0, this translates to x plus 0. In other words, just y equals x. So we're going to have a slanted asymptote that goes to the line y equals x. So our asymptote, if we were to draw it as a dashed line, it would look something like this. Or if we were to draw it as a highlighted line, it would look something like that. So we're going to have a graph that gets really, really close to that line, but never quite touch. Some additional points. Let's plug in some x values. So, we're going to plug in some x values, and then we're going to plug them into x squared minus x minus 2 over x minus 1. So let's choose a couple on each side. So we already know what 0 is. We're not going to have 1 at x equals 1. We already have the point at x equals 2. Let's try plugging in x equals 3. So kind of verbalizing this, well, I'll even demonstrate it. 3 squared minus 3 minus 2 over 3 minus 1. So 3 squared is 9 minus 3 minus 2 over 2. 9 minus 3 minus 2 gives us 4 over 2. which gives us an output of 2. So at x equals 3, our y equals 2. Let me move my picture a second so you can see those points a little bit better. And then let's plug in 4, just to get a little bit, well, actually, yeah, we'll plug in 4. Plugging in 4, we got, I'm just going to go through this a little quicker. We got 16 minus 4 minus 2 over 4 minus 2. 16 minus 4 is 12, minus 2 is 10. So we end up with 10 over, I miswrote something, sorry. It's over 4 minus 1. So we have 10 over 3. When you do that, it's 3 1/3. So it's going to be just a little bit above 3. Yeah, that felt wrong for a second, but that's the way it is. That should be enough. We're going to be able to get a graph for that part. That's going to go, oh, I'm sorry, 3 1/3. I plotted 2 1/3. I was like, something feels wrong, hence my hesitation. So at 4, we're at 3 1/3, so right about there. So this part of the curve is going to kind of get really close to that slanted asymptote there and get really close to this vertical asymptote down here. So it looks a little something like that. Now let's do maybe one more point to the left on the graph. Oh, that's the left on the graph. So the left on the graph. So let's do x equals -2. So when we plug that in, -2 squared gives us 4 minus -2 minus 2 over -2. Sorry, that got a little messy. -2 minus 1. So 4 minus -2 is positive, or is plus 2. So we got 6. Minus 2 gives us 4. And then -2 minus 1 gives us -3. So we have -4/3. So that's going to be -1 1/3 approximately. I think I wrote too many. No, that's right. And so it's -1 1/3, so it's going to be right about there. So this part of the curve is going to get really, really close to that slanted asymptote there and get really, really close to the vertical asymptote there. So that is what this rational function looks like.